point out, everyone, that graph right there is not a graph of petals. That's a very simple polar curve. That makes a circle. That just makes a circle. All right? This also makes a circle. You can feel free to look at it on your calculators. Each one, we know that's just a circle centered at the origin with a radius of 1. And we're going to find the exact area that lies inside this curve and outside this curve. Now this is what it looks like. You can look at it on your calculators too. What's a circle with a radius of 1 look like? Well, it's just like that, right? Here's r equal to 1. You know what this curve looks like? It's very similar. It's a circle, but it's a shifted circle. And that's r equal to 2 cosine theta. You could have made this by hand, Kate, if we just plug some points. My question is, how can we find the area that's inside this curve, but outside the curve with the radius of 1? What would be the setup? Well, just like we've done anything in calculus, won't it have to be a subtraction? Okay. We'll subtract the outer minus the inner. So I say, let's just start, before we get the limits of integration, which I think you're going to find easy now. Can you help me set up the outer minus the inner? What would it be? This area will be, first I got to use this formula here. 1/2, put an integral symbol, but you got to do the r squared minus the r squared d theta. Now who's the outer? This would make sure the answer comes out positive. The outer one's that one way out here, which was the 2 cosine theta. And who's the inner? Just a 1. So far so good? So it would always be outer minus inner, Connor.
When you shifted the circle, did you only shift it over like one space?
That's right. So this thing actually, the center of this yellow circle, the center of this is at a radius of 1. It has a radius of 1, but it's centered at 1. Now if you wanted to graph it, I know I told you I'd give you the graph first. You could have graphed that in probably less than a minute. You would have made a little table. I'm talking about that without a calculator. And you would have just plotted some points. But what you would have noticed was, this doesn't form those petals anymore.
Right.
Because it's not like cosine 3 theta, cosine 4 theta. It just does a nice circle, right? That goes like that.
Thank you.
You're welcome. Someone see that? Like you can just check. At 0, it's a 2. What's going on at pi? Becomes a what? -2 and all that. Ain't cool. Here's the challenge. How do I find those? How do I find the limits? Where are they? In this image, where are the limits of integration?
The origin and the...
It's where the two graphs do what? Just like you did, I think in section 6.1, the very first section of our course. We found the area between curves. We had to find where the two curves met each other. Remember that? You did like substitution. You set one equal to the other. How can I find that angle right there and that angle right there? It looks by symmetry they're going to be the same numbers. How can you do that? What do you do with these two equations? Set them equal to each other. That's going to be our limits of integration. Y'all follow me? Our limits of integration. Where did these two graphs, where did they meet? So we can set that exactly at the point where we do outer minus inner. Isn't that cool? Now, help me solve that. Where do these two graphs intersect? Where do they meet? So we can put these limits of integration. 2 cosine theta must be equal to a what? 1/2. So oh, okay, divide the 2. Who knows those numbers? Is it the pi over the 6 or is it the pi over 3?
Pi over 3.
Is the pi over the 3?
Yep.
When cosine's a half? If that's pi over 3, what would this be then?
Negative pi over 3.
Good job, Isaac. Anyone agree? He says this would be pi over 3. What's the other angle? Down here it's negative pi over 3. Isn't that cool? But you and I are going to solve. This is the last thing we're doing. I was wondering if you could help me solve this with like some. This doesn't have the shortcut this time, right? But does anybody know how I could change this to a 0 because of symmetry? Could you do it? I heard it. I can make this a 0 as long as I multiply this half by what? Let's do it. Don't you hate these? I like when the lower limit's a 0. Let's do it. What's 2 times a half?
1.
2 times a half is 1. What's this squared? Alright, minus 1. Was everyone uncover that? Because see the symmetry? If we go just from 0 to this, multiply the answer by 2, it's going to give us the same answer. You okay with that, Connor? That I did that, I multiplied this. Let's just do twice this answer. You know, from negative pi over 3 to pi over 3, I'll just go from 0 to pi over 3. I'll multiply my answer by 2.
Okay.
And I'm only doing this because zeros are easy to plug in.
Right, okay.
That's the only reason. So you don't have to do this. Some students kind of, they're like, I'll just stay with this. I'll stay the course. And they don't mind plugging in negative pi over 3 at the end. I can't factor a number out this time. What's that trigger then? All right, you ready? 4 times 1/2 plus 1/2 cosine of
2 theta.
2 theta. But you still have a minus what?
1.
1. Oh, we're gonna get this. You want to distribute that now? What do you get? 4 times 2, 1/2 is 2 plus 2 cosine 2 theta minus 1. You see any like terms in there? Anybody see any like terms in there? Before I do the integral? Any like terms? What's 2 minus 1?
1.
Okay. Now I'll go right here. The integral from 0 to pi over 3. 1 plus 2 cosine of a 2 theta d theta. What's that integral? That's theta. What will this become? Sine 2 theta divided by the what? I get sine 2 theta, then you got to divide it 2 by the power rule. What will happen with those 2's? They'll just cancel, right? Look, already, 2 sine 2 theta, divide that 2 that emerges when you do the u substitution. It just keeps happening over and over and over again. So what do we get for our answer? Pi over 3 plus, what's sine of pi over 6? Ooh, that's not 0. And what is the sine of pi over 6? Wait till we get that. What's the sine of pi over 6? Or in this case, sine of 2 pi over 3 first. What's sine of 2 pi over 3? That's which quadrant? Over here? All students take correct. No one's sine of 2 pi over 3 is a positive or negative. It's going to be positive, so the sine of pi over 3 is square root of 3 over 2, then what's the sine of 2 pi over 3? It's also square root of 3 over 2. Everyone okay with this trig? I put that in there. I put that in there. Sine of 2 pi over 3 is this. Minus, oh, this should be easy. What's 0 plus 0? There's your answer. Pi over 3 plus square root of 3 over 2. Kate, any questions on that?
Why was when you got rid of the 1/2 in the beginning, why was cosine squared the other one that was multiplied by 2 rather than cosine squared and 1?
You mean here when it got multiplied by 2 here?
Yeah.
So right here, the only thing I changed it to was I changed that limit to a 0. I changed the limit to a 0 and then multiplied this half was out. So I did 2 times that. So what I did was I changed this to a 0, then I wrote 2 times this half was already for the entire expression. So 2 times a half is what made that a 1. But this was already there and this was already
you
there.
distributed it. Okay.
Yep.
Sorry, I didn't see that.
That's okay. Anyway, so what's that final answer? What's that area? Right there. That area is just simply pi over 3 plus square root of 3. That's the exact area. Area of pi over 3 plus the square root of 3 over 2. Right? If you put a 0 in there and you put a 0 in there, you get the same one. Great job, that's it. That's it for area. So get any questions before you leave? Oh, go ahead.
From that last statement there, that one, how do you get to there, to that next one over there?
So I had 2 plus 2 cosine 2 theta, subtract a 1. So I combined like terms. 2 minus that 1 way at the end, made that just a 1.
Okay.
You didn't have to do it. Like sometimes our eyes don't catch that.
Yeah, I didn't,
And you just do each, you would have had a what? You would have gone 2 theta then you would have subtracted a theta.
Yeah,
This required the use of them.
yeah.
Oh, great job with that. Super job doing this. So remainder class, big stuff.